let's talk about BST removal. All right, I'm going to show you a few examples, okay, and then we're going to determine the theory behind this. So here's some tree, some dummy tree. We're going to just put some values. Okay, so let's look at the theory. The theory, okay, is that we have three cases. When you want to remove a node, there could be three cases. So the case 0, when the node has no children.
Yes, if it's not a parent.
For example, 1.
Okay,
node number 1. So all I have to do is, so notice 1 has no children. There's no left, there's no right.
Yes.
All I have to do is I have to say this one should become equal to
null.
Null.
Yes.
Okay, that's it. We're done. We used to do this exact same thing with the linked list. So this is the. All right. Let's look at the case 1. When there is 1 child. Okay. So for example, 9. Okay.
Will the child be lost or?
So now we have to be really careful. Let's say somebody says go and delete 9. Like, what should I do? 9 has a child. If I remove 9, the child would be lost. We don't want this to happen.
So you have to reassign the child to the parent of the parent?
Yeah. So now we have to look at, 4 scenarios. We have to look at 4 scenarios. How so? Because
right, left.
It can look like this. Can look like this. Okay, it may look like this, or it may look like this. Okay?
Yes.
So this is the node that we're trying to get rid of.
Yes.
Okay, so what should we do? So this is case number 1. So we're going to talk about this thing in a few seconds. Okay, case number 2, case 2, is when there's 2 children. Okay, when there's 2 children. For example, 20, this node, or 8. It has 2 children. 20 has 2 children. Then what should we do? Okay, so it's even more complicated because now it's not just a matter of removing one of the child.
Yeah, which one is bigger than the other, and then
one child. Yeah, so rather we have to discuss, hey, what should we do with the 2 children?
Yes.
So this requires something called finding a replacement or candidate.
So another parent?
So we have to find another appropriate child or a grandchild who's going to replace this node, the one that needs to be removed. Okay? So we're going to talk about this thing. Yeah. So let's discuss case 0, case 1, and case number 2. So case 0 is very easy. Okay, I don't even have to show you any code because it's very straightforward.
Yeah.
Let's talk about case number 1 now. Okay, so here is case 1. Remember the 4 shapes I told you. You can look like
this, and then right.
It can look like this. It may look like this. So there's 4 different scenarios.
And right. Okay, so
we can say this is left, this is left, right, this is right, left, and this is right. Okay, so how are we going to remove this? Straightforward. Let's say this is the node that needs to be removed. Okay, so let's call this one temp. Okay, this is the parent and this is the child. Okay, so all I have to do is I have to say parent dot left equals to child. You agree? So parent dot left. Right now
the
it's
child.
10.
Yes.
But what we're saying is no. Go and do this.
Yes. Okay.
What about the parent of C? Right now it's temp.
So we have to change the parent to. Okay.
So we have to change. We have to say C dot parent
is
equal to P. Okay. So now effectively this is gone. Okay. How about this one? What should we do here? Okay, remember one thing which is very important. You have to maintain the symmetry property.
Yes. So
if temp is smaller than P and C is on the left side of temp, C must be smaller than P.
Yeah, it will be anyway.
Yes, which means it is still valid. Now here you have to be careful.
if the child is bigger than the
Yeah, but doctor, we said that anything on the left of P should even the child or the grandchild should be less than P, so it will be okay.
Very good, very good. Okay, so here what we have to do, we have to say parent dot left equals to C. Okay, and almost the same code. C dot parent
equals to P.
Equals to P. Okay, so what's happening over here is now C was on the right of temp, but now it's going to be on the left side. And C dot parent now becomes P. Okay, let's look at these two cases now. So again, this is the parent, this is the child, this is the node we want to remove.
The same code?
No, not the same code. So we have to say
P dot right equals C.
Okay, and C dot parent
equal P
equals to P. Okay, how about this one? So again, this is parent, this is child.
Same code, doctor.
Exactly.
Equals to C.
Equals C, and C dot parent equals to P. There you go.
Okay, I think case 2.
Here's a hint. If you use a C pointer and P pointer, if you discovered which one is a child, which one is a parent, okay, all you have to do is just write these 2 lines of code, and this will get your things done easily. But now we have to determine what's challenging now. We have to determine, is the C on the left side or on the right side? Okay, which code to run, this one or this one? So we have to put an if condition. Okay, what should the if condition?
If C is larger than
if C is the node C is the same as temp dot left. Okay, if the node C is the same as temp dot left, yani it's this one or this one. Okay.
So if it is, then you do the first case.
So now you have to put another nested condition. We have to check if, okay, because there's 4 cases now. So if condition has to be at 2 levels. So if C equals temp dot left, and now we have to check if temp equals to P dot left. Okay, so this is true. What happens?
We use the first code, doctor. P dot left.
So this is LL, case L.
Doctor, is the first if statement necessary? Like, can we just use the second if statement?
No. Well, what about this case?
If temp is equal to P dot left, then it's like both cases, isn't it?
No. You have,
because it's the same code, like P dot left equals C, and then C dot parent equal P.
So this works basically with this one. Okay. So if it's false, if C is not equal to 10 dot left, which means it's not this one or this one. It means that it must be this one or this one. Okay. So you have to have the else, and there you're going to put the same condition over here.
Okay.
Okay. So it's a nested if. Yeah. If I was trying to write it in nicer, but I think I don't have a lot of space. Let me try to do this again. Okay. So we have these 4 cases. So if p dot left equals to temp. Okay, so which one could it be?
Could be LL or LR.
Good, it's either LL or LR. So we have to check, okay, which one?
If
So
C,
LL or LR.
yes. If temp dot right
So if temp dot right,
equal
I'll go
C.
with the same thing. So if temp dot left equal to C, this means this is LL. Okay? Else,
Yes.
it must be LR. If you go with else, okay, else would mean this is
Either RL or R.
RL or RR. And here we're going to put this condition. If temp dot right equals to C, okay, temp dot right equals to C, I mean this is RR, else should be RL. So there you go. So you have to put this if condition in there to determine which case is it. Okay, some practice.
But then the code will be in there, doctor.
Yeah, of course you have to use this code. This is the code, so you have to use this one. Inside it, you're going to write this code. I did not write the code because the code is here.
Yeah, so it's clear.
So these are the cases. This is LL, this is LR, this is RL, and this is RR. Okay, so practice. Okay, so I'm going to just create some. Okay, remove 4. What should we do?
8 dot left.
Yeah. So
equal to
again, I'm not going to ask you to write code. Okay, so all you have to do is redraw the tree, removing this. Okay, so you're going to say something like this: 8, and the left side is 2. So for me, this is enough. Okay.
Oh.
Another one. Do this one. Remove 10. What should we do?
We just connect the 8 to the 9, and the 9 will be to the right of the 8.
Okay, so 10 has to go.
Yes.
Which case is it? Can you tell which case is it?
RL.
Good. So this is RL. So if I redraw it, I'm going to get 8 and 9 on the right side. Okay. Which case was this one?
LL.
This is LL. Is this okay? Does it make
Yes.
sense to everybody? No? People
yes, doctor, it's okay.
Okay, so let's move on to case number
Case
2.
2.
The 2 children. What should we do if there's 2 children? Okay. Now this is just a little bit tricky, so you have to understand something. Let me try to build a tree, or let's borrow a tree that we've done before. I'll borrow this tree. Okay, so this is some tree, and we would like to remove a node that has 2 children. So example, 17. Okay, remove 17. 17 has 2 children. Like, how do we discover that 17 has 2 children? How do we check? Let's say this is temp. Can you give me an if condition?
Yes, doctor. If temp dot right
If temp dot
doesn't
left is
left
not equal to null,
null
and
template right not
right
equal to right.
is not equal to null. Okay, this means this is case number 2. Okay, what should we do when we have case number 2? We have to remove this. So the solution is we have to find a candidate. Candidate means that one of its grandchildren or children, one of its grandchildren or children, which is appropriate one. I cannot go and...
We have a criteria طيب.
We have to have a criteria. I cannot go and pick any one of them and replace it. No, because remember the boundary search tree must have the symmetry property.
Yes.
The candidate that you choose, for example, if I pick 15, I put 15 over here, let's say. Okay, so would it still be a boundary search tree or not? Okay. We have to be careful about this. What if I pick 13? 13 goes over here. Let's say 13 goes over here. So everything on the left side must be smaller than 13. Everything on the right side must be larger than 13. So what we do is we choose 2 tricks. Okay.
It has to be the first one on the right.
There can be 2 possible candidates.
Okay.
2 possible candidates. The first one would be the smallest on the right side. Okay. Or
the largest on the left side.
On the left side. Okay. So if I'm looking at this one, this is my subtree. This one is my subtree. Okay. So the smallest one on the right side is 18. Okay. Or the largest one on the right side is 15. So these are my 2 possible candidates. I can go with this one or I can go with this one. If you pick any other node, your tree won't be a BST anymore. Okay, why?
Which one's more better? The smallest on the right or the largest on the left?
Okay, just a minute. So if I pick anything other than these 2, your tree will not be binary search tree. For example, if you pick 14, 14 goes over here. So 15 is on the left of 14. That's a problem.
Yeah.
If I pick 19 over here, if 19 goes over here, then 18 is smaller than 19. It cannot be on the right side. Okay? So there's almost always only 2 possible candidates. Sometimes maybe you'll have only 1. Okay? It can happen. It can happen. Only 1 candidate. So now which one should we do?
Yeah, Doctor.
Or should we go left? So it's your choice. You can decide. Either always go with the left one or always go with the right one. So you have to be consistent. Yani, I don't want to mix things up. Sometimes you decide to go left, sometimes you decide to go right. No, that's going to create a problem. Okay?
Doctor.
Yes.
I think if we don't choose one of these 2, it can work, but it will need a lot of work. It will need a lot of changing and movement. And it will be hectic to make this a binary search tree.
Exactly, that's the point. Yani, the whole reason that we're studying binary search tree is because we want to come up with something which is faster than linked list without doing a lot of extra work. So this seems like a good option, that we find a candidate, okay, and then replace the node that you want to remove with this candidate. Okay, so far,
yes.
All right. Now I'm going to show you something which could be interesting. Okay, so for example, we decided to go with the largest on the left side. Largest on the left side. So as it happens, that it is 15. What if this was not 15? What if this was 16? Let's say this is 16. So would this still be a candidate?
Yes, because it's still less than 17.
Yes, but there's a possibility that 16 has a left child. Maybe there's a 15 over here. Is that possible?
Yes.
Yes.
Yeah. Same goes with 18. What if there's a node over here? Let's say there's something over here. Could this happen?
Yes.
Yeah.
Could be 17.
Could also be something over here.
But I don't think the 18 will have something to the left.
Okay, change it. Let's make it 28.
Yes.
Make it 28, make this one 29. Okay, so let's say this is 20 and this is 21. So now your candidate, if you go with this one, smallest on the right side. Okay, so your candidate would be this one.
Yes, 20.
Okay.
Doctor, the keys are always an integer?
Not always. I mean, let's try to understand with integer. It can be anything.
Okay, because if it's not an integer, then it could be like 18 and then 18 and a half or something.
Yes. Or it could be letters or characters or strings or anything else.
Yeah.
Okay. So now in both situations, we have two subcases. Okay. Either the candidate has no child. Candidate has no child. Okay. Or candidate has one child. Can it have two children?
Yes.
Can it have two children? Can the candidate have two children?
Yes.
According to your definition, no. Why? Okay, look here.
Yeah, no, it will
If
cannot.
there was something over here, then this will not be the candidate. This will be the candidate because we're looking for the largest on the left side. This will be the largest one. Same goes with this side. You're looking for the smallest on the right. So if there was something else over here, okay, then this cannot be the candidate. This will be the candidate because this would be the smallest on the right. All right. So let's stop here for a second. Now we have to decide which one you want to do. You want to do this one or you want to do this one. We go with smallest on the right or largest on the left. We cannot implement both of them. Although the idea is similar. If you want to implement them, you can also implement the other one or vice versa. But we should not implement both of them. We have
In this tree, I think smallest on the right would be nice.
And
okay. So usually what we do in my class is we pick this one. Okay, we go with smallest on the right. So again, like I said, it doesn't have to be this way. It's up to the programmer, the developer, or the software engineer to decide which one to go. So it's your choice. So in my class, we just always almost pick this one. Find the smallest on the right side. Okay, let's see what we have to do now. So we have two scenarios. I'm going to build the two scenarios. Okay, let's say this is the node 10. Okay, let's say I'm trying to remove 12. Remove 10. Okay, so we have to find there's something up over there. We don't know how many other nodes are there as parents of 10. So we have to find the candidate. But according to what we've decided, we'll find the smallest on the right. So by that definition, my candidate is 12. This is candidate. Okay, this is the one that needs to be removed, 10. So what do we have to do now? What should we do?
now
20 should point to 13.
Okay, we have to remove, first we have to get rid of this node. We have to disconnect this. Okay, so first I'm going to look at the scenario where this does not exist. This is not there.
Okay. Then you just
So candidate has 0 children or child. So this is the scenario. So now what we have to do is we have to say
temp
simply remove this one. Okay, so we're going to say candidate. First, we have to disconnect this, right? Because we want
Yes.
to get rid of this. So you're going to say candidate dot parent dot left. Okay, candidate dot parent dot left equals to now. So now this becomes disconnected. This connection is not there anymore. Now, what we have to do is we have to put this over here. We have to put this over here. Okay? But to put this over here, what do we have to do?
Candidate dot parent
Okay?
equal temp.
Candidate dot parent equals to temp dot parent. Okay? So candidate
We are
parent.
removing the 10 or
Yeah, we want to remove the 10.
yes.
So we're saying candidate dot parent now becomes whoever is the parent of 10. Okay. Next. Next.
Temp dot parent or candidate dot parent.
No, first prepare the candidate. Okay, before you remove 10. First prepare the candidate. What about the left and the right of candidate?
We will move 20 to be the right.
Temp
Candidate dot right
Candidate dot right
is
equal
equal to temp dot right.
temp dot right. Okay. So
Then
we also do this thing now. Temp dot right is taken place. There's nothing on the left side. That's for sure.
But we still should put the condition in case, right?
We're sure about this thing that there's nothing over here because candidate is the smallest on the right side. We're sure there's nothing here. We don't have to worry about it. We have to worry about the right one. So now we're saying candidate dot right equals temp dot right. So this is temp dot right. Yani, now we're going to put 12 over here. 12 dot right becomes this one. 12 dot parent becomes this one. Okay, we don't have to worry about the left side. So your node is ready. 12 is now ready. Now what we have to do is we have to disconnect temp. Okay, how do we disconnect temp?
Temp dot parent
dot right.
right equals to
No,
null.
we have to change this one. We have to say this guy. Dot
Ah,
parent.
okay. So this guy dot
Temp dot temp dot right dot parent
Dot parent
equal candidate.
equals to candidate. Very good. Okay, so we've disconnected this one. Now this does not exist. But one thing is missing, one thing is left. Can you tell me what?
We still need to the parent dot right.
This one we have to do.
Yes, equal
Okay.
candidate.
So we
Temp
have to say temp
dot parent
parent.
dot right.
Okay, left or right?
Right.
We don't know. In this shape, maybe this is true, but maybe the shape is different. So it's either left or right equals to
Candidate.
candidate. Yeah. Okay. So there you go. We're done with this. This is when we have 0 children. Okay.
So how can we know? How can we know if it's on the right or the left?
Well, we have to check. We have to put an if condition. Okay.
Okay.
We'll let you check if it is on the left side or on the right side. So you can put an if condition over here to check that. Everything else will be exactly the same. Okay, now let's look at the scenario where the candidate has the child. It can be only one child, cannot be 2. So imagine this one existed. Okay, this one is there. So 13 is there. Okay, so what should we do? Remember, the code is going to be entirely the same. We just have to add a few more lines, which is we have to disconnect this first.
and then reconnect it.
And then reconnect it. Okay, so what I'm going to do is I'm going to call this one. I'm going to call this one something. Let's call this thing X.
Okay.
So once you're done with all of this, okay, once we're done with this, we have to reconnect this. Okay.
So we do x dot parent.
So what we have to do now is we have to remember this one.
Okay.
So we're going to call this one y, for example. So after all this code is run, we're going to say y dot left equals to x.
X.
Okay, that's it. Just one extra line.
Doctor, this is just to make the code look better, right? Because like we could just use the normal, like, I don't know, candidate and other variables that we have.
What do you mean? Yeah, of course. Yeah, you can say this thing, whatever this node dot left dot 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 left dot dot. Yeah, you can do that, but this is easier, makes it nicer. Yeah. So that's it. That's good. That's going to take care of the two cases. Sometimes we call this case as double deletion. Okay, double deletion, because you're basically, when you're trying to delete 10, we also remove 12. Okay, so you remove this one and then replace it with the other one. That's why sometimes double deletion. If this is clear, let's look at an example. Let's see if we can work with the example.
Doctor, can you just go back for a sec?
Yeah.
Candidate.parent.left. Which arrow, or like, how does it point?
So this is candidate dot parent dot left. Okay. So what we're saying is this one.
Okay.
Dot parent dot left. Okay. We delete. That's what we want to do. We want to disconnect it.
So if we have the y, it could be y dot left, and that's it.
Of course, yes.
Okay.
Yeah, or you can say y dot left equals to null.
Okay.
So I'm going to use the same tree, and let's see if you can do some practice for this. Okay, let's get rid of 8.
Okay.
Which one is a candidate?
That will be
The smallest on the right.
4. It is 9, Doctor.
9.
Is 9. Okay, 9 is the candidate. But if I want to redraw the tree, what's going to happen?
9 will be the root.
This will become 9, and this goes away.
Yeah, and 10 will be pointing to null.
Of course, 10 dot left would be null. This becomes empty.
Mm-hmm.
Okay, now remove 17.
17. Okay, so the smallest to the right is
12.
Or
Small
18.
to the right. So sorry, small to right. Yeah, you're right.
18.
18. Yeah, it's 18.
So remove 17. This is 17. Okay, candidate would be
18.
the smallest to the right, which is this one.
Mm-hmm.
Okay, so what's going to happen now? 18 goes away. This becomes 18. Okay, and that right would be 19.
19.
So basically, it's not deleted. It's just redrawn. Okay, let's remove 4.
Okay. Smallest to the right.
5, Doctor.
5, yes.
Smallest to the right is 5. This is the candidate. So simply replace this with 5, and this goes away. Okay. So this was just a little bit of practice for.
I think, Doctor, if the candidate has no children, it will be the easiest case.
Yes.
If our candidate.
For example, remove 1. Okay, what do we have to do? Remove 1. This is 1.
Just point 2 to null.
Yeah, just point 2 to the left becomes null. That's it.
Mm-hmm.
That's the easiest. Okay, remove 14. Can we do that?
14, yes. Okay. It's 1 child.
This is 14.
So yeah, just point
So just remove this one.
13. Yes, you point 13 to 15.
15. Okay, that's all. So in the exam, I'm not going to ask you to write code to do these things, okay, because it will take longer. So what we do is we just go with the illustrations. You have to show it step by step, what is deleted, how this is deleted, which case applies, and so on. Okay.
So I have to draw and redraw the...
Yes, you have to draw, you have to redraw, you have to redraw. Yeah.
So, Doctor, isn't it the same code? And if it's we only have the 3 cases, so for each case there is a code, and then it's not changing. It's the same code.
Of course, yes. But logically, when we want to see, what's going on, okay, so you have to redraw the tree and then redraw it and redraw it. So we know that you're following the right process. Okay, so we're going to look at this thing now when we do the tutorial. So, by the way, we're done with this topic. Let me show you the code for this. Okay, so again, we go to trees in the GitHub source. Here's the binary search tree, and this is the binary search tree class. So last time we looked at the basics of this class. So we had the insert method, we had the search method, then we had the traversal. I showed you that this did not work. So we had the recursive solution, which is for pre-order, in-order, and post-order. That's easy to remember. By the way, just for your information, I have given this previously in one of the exams because it's very easy to write it. Okay, and here's the removal method. So let's go over this thing very quickly. Okay, now first we check, of course, if the tree is empty. If it is already null, you should not go and remove anything from there. Okay, and here I'm calling the search method. The search method goes and finds a node. If the node is found, okay, we'll continue with the deletion. If it is not found, we simply return false instead of wasting over time. But if you found it, now we have to determine which case is it. So first we check if this is case number 0, which means there is no left child, there is no right child. If this is the case, we simply make it null and return. Otherwise, now we have to check if this is with 1 child. If there's 1 child, I told you there was a nested if condition. So we can have a nested if like this, okay, to determine which case is it. Should we go right, 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 left, left, right, okay, or right, right. If not, then it must be 2 children, okay? So what I've done over here is just to explain. If you remember, I told you many times before, this code is just to use in the class. And we use this thing just to explain things.
Mm-hmm.
So here's more explanation for that. There's 3 cases. There's no child, 1 child, and 2 children. So this is the case when there's no child. That's what we're going to do. Okay. If there's 1 child, okay, here's the code. So these are the 4 scenarios, 4 cases. Okay. And this is the case when there's 2 children. So we have either candidate has no children or candidate has a right child. Okay, so this is just finding the candidate. Once you've found the candidate, okay, these are our scenarios. You can look at the code. Okay, it has no children. And this is the last scenario when it has a child. Now, either there's 2 situations. Either the candidate has a child on the left side or on the right side. So this is the code for that. And at the end, of course, once you remove something, size minus minus, and we're going to return true. So this is not a very well-written code. If you're going for a very good quality code, then look at the code that I've showed you in the slides. Okay, I'll show it to you now.
Doctor, if you want to remove the root itself, we just have to follow the same steps?
Yeah, if it is, so you have to be careful because now the candidate will become the root.
Yes. We just have to change the root in the case of the root.
Yes. So if you look at the book, okay, they've described 2 approaches. The first one is a lazy approach. So what we do is simply make your node dead. We actually do not physically go and remove the node from the tree. The node stays there, but we just leave an extra dummy pointer there saying that this is a tombstone. Tombstone means that this node is dead and we should not visit it anymore. Okay, so this is one solution. It's called the lazy approach, but it's not very efficient because after a while, okay, if you keep removing everything from the tree, your tree still exists, but it's going to contain lots of tombstone values. So this is not a very efficient approach. The other approach, the one that we've just studied now, is called the Hilbert deletion. Okay, it's formally called Hilbert deletion. So we look at the two tree cases for this. And this is the Java's implementation according to what is given in the book. Okay, so this is the entire delete method. So compared to the code that we've put on GitHub, this is much, much easier to look at. But remember,
yes.
This could be recursive. Okay, it can be recursive. So you have to be careful when you're looking at this code. Right. Look at the simulation. Now we're discussing the problem with Hilbert deletion. Remember I told you that whenever there's two nodes, there's a possibility that we go find the smallest on the right side or find the largest on the left side. And we said, no, we're always going to decide to go right. We'll find the smallest on the right side.
Yes.
So what happens now is if you simulate a tree using this approach, after a while you'll notice that, okay, the right side of the tree is always smaller in terms of height or number of nodes than the left side. And if you keep repeatedly removing nodes
from the right,
have two children from the right side, okay, eventually your tree is going to look like this. It's somehow skewed to the left side. Okay, so this is a problem with this approach, the Hilbert approach.
but can you control it, doctor?
It's going to give you a binary search tree, but it's going to be somewhat skewed to the left side. Okay? Which means that we're not guaranteed to get a log of n time. That's what we were hoping for.
Yes.
Not going to get a log of n time. It's going to be more than log of n, but less than n, hopefully. So bottom line is, if somebody's asking you, give me a guarantee, what's the worst case runtime for binary search tree? Okay, I cannot make
worst case.
Worst case. I cannot make them happy. I cannot say that it's log of n. Because for insertion, there's a possibility the tree could look like a linked list. So the runtime would be big O of n. Same goes with the removal. If I'm using the Hilbert approach, the one that we've studied, okay, that may also give us a kind of a skewed tree, which means that runtime would still be big O of n. Okay. So after doing all of this work and rework, okay, we're going to have the same dilemma. The runtime worst case scenario for binary search tree guarantee is big O of n. But if we do experimental evaluation, we'll notice that the runtime in reality is much faster than n. Okay, it's much faster than n. But of course, we cannot get log of n. It will be slower than log of n. Like one other thing, because of the nature of the Hilbert deletion, okay, according to the runtime analysis based on experimental evaluation, we can say this thing on average, the deletion takes square root of n time. Square root of n time. Like what's a big O for square root of n?
N.
Good. Still big O of n.
Yes.
Okay. So this means we're not really happy, even for the average case. Okay. For search and insertion is good enough. It's something close to log of n. But for deletion, it's something close to big O of n. Okay. So this is not really a lots of improvement on top of the linked list, where the linked list takes exactly a maximum O of n time. All right, so that's
Doctor, there's no algorithms that could stabilize like how the tree goes when you delete stuff?
No, we're going to see this thing, inshallah, from next class. We're going to talk about EVL. The EVL guarantees that your tree stays almost a complete tree.
Okay.
We'll talk about it tomorrow, inshallah.